much faster than I expected, so we still have time for kind of small recap. If there are some points that were unclear or where I went too fast, maybe we can explain them again. So I don't know if there is already a question or some point you want to see again. About was the cross-function algorithm for VASS clear or not? It was clear? Okay.
Some people are still missing. So.
Ah, yes. Okay, so we wait.
Maybe it wouldn't hurt if you recall
yes.
The rules.
Yes, while we are waiting, so I recall the rule. So rule 1 was to add the weight of simple positive cycle when they are executable. So it's the simplest one. And then rule 2 was something somehow similar for negative cycle, but of course you cannot add negative cycle, so you do something with them. And the thing you do with them is to construct vertical or horizontal vectors when you don't have them in the period set, and when you can construct them with the negative cycle and with some period. So I think this part is clear. And maybe more complicated are rule 3 and 4, but they are not so important in the termination proof. As you see, we use them in the preliminary steps and not at the very end. So the rule 3 was to do something when the period set is empty, and all you need to remember is that it's used so that the set of period is not empty on a branch, and this kind of, so this is not very crucial. You don't really need to understand this rule. And this one was slightly more useful. It was used when we wanted to prove that every vertical or horizontal line only has finitely many bases on it in the branch. Is there something that needs to be recalled?
So it's like to be sure. So you add b minus b prime to the periods, right?
To the set of periods, yes. Yes, I added to the set. I don't add this to the period, but okay. Was it some for the cross-function for branching VASS was something unclear or too fast? Okay. Okay, so we start from the initial configuration. So it's a linear set with only one vector, and even before treating the node, we already have a new transition, which would be the transition related to the node 0. In general, you could have several transition plus p. So if you have several transition plus p in the branching VASS, you would have several transition 0 here. Then you add the periods according to the 4 rules in this VASS. So this transition behaves like a transition of displacement 0. Then when the periods are added, this transition is modified because it's really related to this node. So the displacement will be whatever is in this node, and this linear set is a shorthand. You should imagine that we have an intermediate state with a loop free, and we have 0 on 2 transitions here. Then we create children as in a cross-function. Do I need to explain this or? Okay. Then we treat node 1. So when we treat node 1, we add this new transition 1 with the semi-linear the linear set contained here. And then we treat node 2, and the difficult part was about the children of node 2, because we have 3 outgoing transition, one which is a normal transition with displacement 2, 1, so there is nothing special about it. You create 1 children, and these 2 transitions, the situation is a bit more difficult, so I will explain this again. We start with the 0 transition. So it's labeled by a linear set, but what we do is that we imagine that there is an intermediate state with a loop free, and we ignore this loop free. We just move through the 2 transitions at once. So we do nothing with the period, but we add the basis as if it was the displacement of the transition here. So I create a new node 4. It has the same basis as the node 2, just because the displacement is 0 here, and it is in state P. And it has 2 parents in the DAG. one parent which is also a parent in the tree, somehow the main parent, which is node 2. And there is a second parent, which is here node 0, because I went through the transition 0. And one important point that I forgot is that in some situation you could have here the set of period of node 0 is included into the set of period of node 2 because 2 is a children of 0, but we could have, it could be maybe node 3 and maybe node 1, and maybe node 1 could have a period which is not here, and in this case we add the periods of both parents. So somehow you can imagine that the periods are moving along the edges of the tree and the edges which are in the DAG but not in the tree. And we do the same for the transition labeled by 1. And then my execution stopped here.
Now, I have just maybe an observation that can be helpful for the rest of the talk. Is the fact that at some point in the Prof-Pensio algorithm, we are adding the effect of positive simple cycles.
Yes.
And for the VASS extension, as you mentioned, we are going to put some kind of linear sets in between states. But when we are going to consider positive cycles with this linear set, we are just considering the base of the linear.
Yes.
It's because somehow it's no longer a simple cycle if we use the periods.
Yes, exactly. So yes, it should explain about rule 1 when I say the weight of positive cycles. If there is a transition like the transition 3 in the cycle, we don't care about the period here. We only look at the basis, and we do as if it was the transition here of weight 3, 4.
I had a question also about why is it useful to use both the transition 0 and 1? Because you know that 1 is a stop node. It's 0.
Okay, so we could remove this transition, exactly. I just choose to let it because I wanted the description of the algorithm to be as small as possible, but of course it is useless. Okay, so there was some modification to the rule for adding periods, but we don't need to see them again because they were like very technical and it's very hard to understand where they are from. So you must just know that we have the same rule as Coft and Pensio, but with slight modification. Then there was this part, but I don't know if you want me to tell it again. We won't use it in the following. Just there is some simple proof that the first algorithm terminates if we manage to prove that the second one terminates. Then there was the termination proof of Coft and Pensio. So if there is a point that you want me to say again, you can ask. But otherwise, I will just recall the most important things. So we just had some prerequisites, but they were not very important and difficult. At some point, we managed to have an infinite branch with same state and same set of periods, and we want to see that the stop condition applies. And the set of periods is not empty. Just, we had the lemma. And in the end, we thought that the only thing which is needed is to prove that this set, which is every configuration that will be found in some node of the sub-branch, this set should be included into some cone generated by the set of period P, and the basis that we will choose for the cone will be B and 0, so the very first basis of the sub-branch. And here this claim is not so important. Skip it. And what is important is the technique of the proof for this fact. So we want to prove that the difference between two bases is included into some cone. And we view this as a cycle, as the weight of a cycle in the VASS. The reason why it is the weight of a cycle is that when you go from one node to the child, you apply some transition. And we are at some point where the contours are high, so we never add periods, we just add the displacement of the transition. Then we decompose this into simple cycles so that the weight of the big cycle is the sum of weights of simple cycles. There could be many decomposition, but the decomposition chosen is not important. Then we use rule 1 and 2. So for this critical part of the proof, only rule 1 and 2 of period are used. So the rule 3 and 4 are somehow not so important, they are just for the prerequisite of the proof. It's easy with rule 1 to show that the sum of the weight of positive cycles is in the cone. And then there was some kind of difficult argument to show that when you add the weight of a negative simple cycle to some point which is in the cone, you cannot leave the cone. And if you prove this, yes, I forget to explain this, you can use this lemma several times. You use it for the first weight of negative cycle, then you have a new point in the cone, then you use it again, and you use it once for every negative cycle, and at the end this whole sum will be shown to be in the cone. So here there was a kind of geometrical reasoning. It's not so important to understand it, but you just need to know that we use this period 2, and this period 2 allows us to say that the weight of a negative cycle doesn't make you exit the cone. And that was the end of the termination proof for Hopcroft and Pensio. Is there any question? No. Okay, perfect. So now we are going to see the termination proof when we extend the algorithm for branching VASS. And the termination proof will be very similar. So what I do is that I will once again make a list of every step, and for every step we will try to see if the step is still true or not. So the first thing was to suppose for contradiction that the tree is infinite. So here it's not exactly a tree that we have a DAG which is covered by a spanning tree, and this spanning tree has finite index. So once again we can apply Koenig's lemma and say that if the graph is infinite, then we have an infinite branch. So this is an infinite branch in the tree, in the spanning tree of the DAG.
So by spanning tree, you consider this not dotted rule,
yes.
Arrows,
yes.
but just
the arrows that are not dotted in my presentation. Then you can also take a sub-branch where every node has the same states. That's just easy because there are finitely many states. And then the second point was to prove that the set of periods become constant in the branch from some points. And the argument was that first the set of periods is a growing sequence, and the second argument was that there was a bound on the number of periods that you could add at one node. And now it's not true anymore because of the first. There are two reasons. The first rule is that you add the weights of simple positive cycles, but now the VASS is growing. So you could create new simple positive cycle during the algorithm, and this could cause non-termination. So that's one problem we need to solve for branching VASS. And there is a second, more subtle problem, which concerns every other rule, even the simple rule 3, which says that you add a period when the set of periods is empty. The problem is that now, I said it very quickly, the periods are transmitted along the edges of the tree, but also along the dotted edges, which are the edges of the DAG. When you apply, when you go through some transition related to node K, you inherit of all the period of node K. And so what could happen is that in the Hopcroft-Pensio algorithm, you only have the period that were created at one of your ancestors in the tree, in the branch. But now, you could inherit from periods that are created outside of the branch you are considering. So in this example, you consider the green branch alpha, and here you will inherit from every period created in the red nodes. But you can see that the red nodes are not part of the same branch. Like if you consider the DAG as an order, they form an anti-chain. And so, since they are not comparable, it could be the case that the set of period is empty here, and so you use the rule 3 once here, and once here, and once here again. So actually it's not, in this example, it's not the case, really, because if you use rule 3, so the rule when the set of periods is empty, if you used it infinitely many times, it would mean that the set of periods is empty in this branch, and we saw already that it was impossible. But if you have some more complicated tree, or if you take some other rule for creating a vertical axis, it could be the case that you create a vertical axis here, and a different vertical axis here, and again here, because you never have a vertical axis here, and then this branch will inherit from all periods. So we will need to do something about this graph to ensure that this bad situation doesn't happen. Continue with this. And then, basically everything we did will still apply in branching VASS. So we proved that the set of period was never empty in a branch, and this is still true. It's just some well-quasi-order fact. Then we showed that there could be only finitely many bases on each vertical and horizontal line. So for this part, I didn't write the proof, but it was just a consequence of the rule of period 4, and this will be true again. It's really not a problem. Then we had this last step, this crucial reasoning, when we wanted to prove that every basis was included into the cone with this generated by the set of period and the first basis of the sub-branch. And these steps will still be true. There's no problem. And also the lemma, of course, is still true. So really the only problem is to show that the set of periods will become constant from some point in an infinite branch. So you can be very optimistic and say, okay, we almost apply the same proof, or you can be quite pessimistic and say, in fact, this point, to prove this, will be more complicated than the whole Upcroft-Pensio termination proof. So there's one small remark I need to make, because before this, we want to prove that in some infinite branch you only add finitely many periods, but we need to explain precisely what is an unnecessary period and when exactly you add a period. Because it could be the case that, for instance, you already have the period 1,1, and some rule allows you to add the period 2,2. But in this case, you say, okay, I don't care, because 2,2 can be obtained by adding twice the period 1,1. Adding it won't change the linear set, so we don't add this. So there are some unnecessary periods. And the important idea is that you can be even more restrictive than this. Not only we will forget about every period which is already in the additive closure of the set of periods, but we will also not add periods that are already in the cone. So here the argument is more complicated. You need to go through the whole termination proof of Upcroft and Pensio and see that we never really used the value P star, where P is the set of periods to which the branch stabilizes. We only used the value of the cone. So we don't really care about what will be the final value of P star in the branch. We only care about the final value of the cone. And so if you have a new period which is already in the cone, you simply don't add it. And now it's very clear what is the condition, what are unnecessary periods, and when a period is somehow dangerous. So the periods that are dangerous are those who are out of the cone. They can be below the cone or above the cone. And the problem is when periods are going increasingly closer to an axis, but you never add the axis itself. So you don't want your cone of period to enlarge infinitely many times. So that's about unnecessary periods. But I think for comfort, we will stick to the rule that a node inherits from all periods of its parents. So it's possible that a node contains unnecessary period. If you are in this situation, you just keep both periods. I think this point is not so important, but I prefer to do this way. So now I will explain, I will give an overview of the proof. The idea is that there will be two very different kinds of arguments. There will be a kind of global reasoning, or in other words, a reasoning about the structure of the graph of the Upcroft-Pensio DAG. So this is completely new. There was no such argument in the proof of Upcroft and Pensio because it was unnecessary. Like they only had a tree, and it was very simple. A branch had only period created at some node in the branch. So there was no need to study the structure of the graph, but now we have a very strange data structure, which is a DAG with a spanning tree. So we need to study a bit this structure. And this argument will be about how to choose. In the classical Hopkins-Portier algorithm, you suppose for contradiction that the tree is infinite, and then you pick with Koenig's lemma an infinite branch, but you choose this infinite branch arbitrarily. Now what we will do is that we won't choose the branch arbitrarily, and if you choose it very well, this branch, the graph will have a nicer structure, because you only care about the node which can reach your infinite branch. These are the nodes from which you inherit periods. So if you choose the branch alpha very well, the reasoning will be simpler. And this kind of argument will be for the problem. Maybe I can just go back to the slide. It was about this problem, the fact that when you have an infinite branch, you inherit from periods that are out of the branch, and that this period created out of the branch could be created at nodes that are not on the same branch, nodes that are completely independent with no relation between them. And also, I will just have this notation. The nodes for which there is a path in the DAG to the branch alpha, I call them the predecessor of the branch alpha, and I write them pred alpha this way. So this structural argument will be very useful, but they won't be enough to prove that rule 1 doesn't create infinitely many periods, because we still have this problem that infinitely many positive simple cycles could be created, and even if we are very wise with how we choose the branch, this has nothing to do with the positive cycle that appear in the graph. So we will need to have a second set of arguments, which I call the local reasoning, and it's very close to what Hopcroft and Portier did at the very end of the proof. So it was the moment when we took the difference between two bases in the Hopcroft-Portier DAG, and we expressed it as the weight of a cycle in the VASS, and then we decomposed it into simple cycle. So we did this kind of argument, but it was much more difficult in our case. So maybe I can explain what is difficult about them. So here you have point 4. The point 4 says that finitely many bases on each vertical and horizontal line, there are just finitely many bases, and this allows you to suppose that from some point in the branch, both counters are very high, and when the counters are high, everything in the branch is simpler, and that was how we could decompose the cycle into simple cycles, and said that all of these simple cycles were executable and apply the rules of Hopcroft and Portier. The problem in our situation is that this point 4 can be proved, but only once you have already proved point 2. You cannot prove this directly. The problem is that when the set of periods is not constant, you could have infinitely many nodes that have exactly the same basis, and so the contour could remain small because you go infinitely often on the same basis. So we have this problem, and this means that Hopcroft and Portier had this hypothesis which made everything simple, and we won't have it. So that was the problem here, but I think we won't talk a lot about this part because it's very technical, it's not really new. We'll talk much more about this part. So what we want to do is choose a good infinite branch among all the possible infinite branch. Like we are doing the proof by contradiction, so we suppose that the graph is infinite. So it's a bit strange. We are talking about objects which will prove in the end that in the end will not exist. So it's really abstract. So how are we going to choose the best branch for our reasoning? The idea is that we will define the quasi-order on the infinite branch of the tree, and we will choose a minimal one. So what we want to do is define a good quasi-order, and then we need to prove that this quasi-order has minimal elements. So the quasi-order that we took is that a branch alpha is smaller than a branch beta if every node in alpha can go to some node in beta. So here I made drawing for the three cases. Here is the cases where alpha is strictly smaller than beta. So it is the case that every node of alpha can go to a node of beta. It's very simple because here the edges are horizontal, but they could be like this or more in diagonal. But here you can see that when you are in a node in beta, you cannot go to a node in alpha using full or dotted edges. No possibility to come back, so we have alpha strictly smaller than beta. Here in this situation, when you are in alpha from depth 1, you cannot go back to beta, and similarly, when you are in beta from node 1, you cannot go back to alpha. So the two branches are incomparable. And here you have two equivalent branches, so this quasi-order is not an order, because you can always, when you are in beta, you can always go to alpha, no matter how deep you are, and similarly for alpha. So the intuition is that when you are in this situation, you want to study alpha rather than beta, because beta will inherit every period from alpha, so it will only be more difficult to study the set of periods in beta. In this situation, you don't care about alpha or beta because they don't exchange periods. And in this situation, you also don't care about the order, but for a different reason, because they will have the same set of periods, they exchange all of their periods. So now we need to prove that there is an infinite, minimal infinite branch for this order. So I don't give the proof. It's not very complicated. I think all of the situation is somehow summarized by this drawing. Here what you can see in red, orange and green is the beginning of an infinite decreasing change for the quasi-order on branches. So this branch, orange, is strictly smaller than the red, and this branch, green branch, is strictly smaller than the orange, because you can always use this horizontal line. So this proves that the quasi-order under study is not well-founded. So very often when you want to prove that an order has minimal elements, you actually prove that it is well-founded, because well-founded implies minimal elements, but here we cannot do this. But we will still have minimal elements, and the idea is that if you have bad luck and you have an infinite decreasing chain of branches, you can build a minimal branches out of this infinite decreasing chain. And the way to do it is that here the branch beta will have, for the branch beta, you always use edges that are used by infinitely many branches of your decreasing chain. So you can do it because the tree is finite, has finite branching, and so there are always minimal branches. That was the first point. Then I will explain why this order is, how to use this, the minimality of this order. We saw that intuitively it was reasonable, but now we will prove some results. So this characterization is not hard to prove, but it's a kind of proof, like a two-line proof, but you need to have understood well every definition in it, so we'll try to explain it. This characterization says that for every node which is a predecessor of alpha, every node which can go to the branch alpha, not necessarily in the branch, it is the case that this node n can go to every other node which is also a predecessor of alpha, except finitely many. So the good situation is the one on the right. Here you take one node n, it is in the branch, but I could have taken this node, for instance. And here you can see that there can be some nodes on the right which are not predecessors of alpha, so we don't care about them. Here you have nodes that are predecessors of alpha to which n cannot go, but there are only finitely many, and then n can go to every other predecessor of alpha, which will be somewhere in this part. And on the left, it is the situation where alpha is not minimal. So here you can see that you have the node n, and you can have infinitely many nodes to which n cannot go. They are here. But out of these nodes, you can construct a branch, because somehow these nodes form a subtree of finite index. So if there are infinitely many nodes, predecessors of alpha to which n cannot go, you could construct a branch which is smaller than alpha and to which node n cannot go. So it would be a branch strictly smaller than alpha, and this would contradict minimality. So we have this property, and this implies that this, or maybe I didn't explain the notation, I hope it is clear. This arrow with a G here means the edge arrow in the DAG, and when I put a star on it, it means the path relation in the DAG, and here I just cross it to mean the negation. So this relation, it's a path relation in the DAG, but you should read it as an order. So a node is smaller than another node if there is a path to the bigger node. And so this order, when you restrict it to the predecessor of a minimal branch, it has this strong property, and this, in particular, this property means that there is no infinite anti-chain of nodes. There is no infinite set of nodes, so that in this set there's no path. There is no path from between the two. So that was the characterization of minimal infinite branch. And now I will just explain how we use it. So we will prove that rule 3 cannot create infinitely many periods that are inherited by the branch alpha. So you don't need to remember the rule 3, just it says add something to the set of periods provided that it is empty. So now, if there is a path from node n to node m, then the two nodes cannot use both this rule, because then node m inherits from every period of node n. So if you use the rule at node n, it means that the set of period at m is no longer empty, and you cannot use rule 3 again. So this point here can be reformulated as the node where a period is created by rule 3 are an anti-chain, a set of incomparable nodes for the order, which is the path relation in the DAG. And just like the characterization of infinite, characterization of minimality for an infinite branch was exactly that. No, it was not exactly, but it implied that there is no infinite anti-chain for this order among the predecessors of alpha. So in other words, only finitely many periods are created by rule 3 and can be inherited by the branch alpha. So there is a similar reasoning for rule 2 and rule 4, and so it means that just by choosing the branch carefully, we avoid the creation of infinitely many periods by the easy rules. And now we need to prove that rule 1 doesn't create infinitely many periods, which was really the most difficult part of the proof. So I will not explain it in all detail, it will be very a gross simplification. The first thing you need to do is to somehow describe all the cycle, all the simple positive cycle that will be created in the VASS. And to do this, we will, so maybe the algorithm goes like this, you create new transition a bit. And to describe the cycles that appear here, we will describe them from the simple cycle in the branching VASS. So this branching VASS, it doesn't change. It has finitely many cycles. Here you can view them. There is one big cycle here. There's a smaller one which uses this transition here.
Clotilde, could you recall what you want to show now? This is for
It's
rule 1, right?
It's not very easy to express it. I want to give a description of the cycles, all the simple cycles that may occur in this VASS, a kind of notation for them or a way to organize them, to partition them into finitely many sets. And for this, I will use the cycles inside the branching VASS. So I think about, I look for the cycles using this transition and also the edges, like the red and green edges. I take them all and I just look at the cycle that I obtain. So here I have 4 cycles, there is one here and also this small loop here. And then I can just number the position. I could say, okay, this is position 1 in cycle C3 and this is position 2. And then I can describe all the cycles here with a kind of polynomial notation. For instance, with this pink cycle will be C3 of 1 and 3 because it corresponds to the cycle C3 in the set of period, but we replace the notation, the transition the plus P here by the transition related to node 1, and here we replace the transition plus Q by the transition related to node 3. And we could also have a cycle C3 of 1, 0 if we used this transition instead of the transition 3. So every period in the VASS will be obtained in this way by taking a cycle in the branching VASS, there are finitely many of them, and replacing the double arrows by the transition of some node.
So what C3 of 1 and 3 means? So could C3 of something else be valid?
Not every C3 of something is defined. If you give me C3 of 2 and 3, it's not defined because 2 is a transition here, it's not a transition from Q to R. So it should be a transition from Q to R because the transition plus P is from Q to R. And also it should have been, at the moment where you add this transition 1, you add this because it is state P. So it should be, like 1 should be any node which has state P. Because here, in the cycle, the first transition is the transition plus P.
In fact, so C3 somehow it's like a cycle in a vector addition system, but you have variables. And C3 is moving from R to Q, adding P, and then moving Q to R, adding Q. So you have two variables, P and Q, and you need to assign those variables with some values. And in order to remember which value we consider, we put the numbers 1 and 3.
So the variables can take what values?
It
So
can take the value reachable during the exploration of the DAG, corresponding to the right control states. So, for instance, I think C3 1 is because it's why it's 1? I can't remember. It's 1. Because 1 was something.
It was some node in the DAG which is of state P.
Oh yes, this is a node.
So to summarize, you can view every cycle in the VASS, every simple cycle, as arising from some cycle in the branching VASS, and here there are finitely many cycles, but just you replace the transition with double arrow, like plus P, by some transition created from a node in the DAG.
So the 1, it's like stands for the node number 1 in the DAG.
Exactly.
Yes. Okay. Yes, I don't write the label here, but there should be some linear set here. And just I write 1 because it's the number of the node from which this transition is coming.
So if you took a longer cycle from the branching VASS, you would have like 3 or 4 tuple, right? 3 or 4
yes.
variables? Okay.
And the idea is that it makes no sense to compare a cycle which would be like C1 of something and something with a cycle which is C3 of something and something, because there are only finitely many cycles here. So we will compare all cycles of the form C3 of some things together, and we will compare the cycle C4 together, etc. Just you need to organize to see which cycle you compare with which cycle, because we want to prove that only finitely many cycles will be useful, will create new periods, and want to prove that all the other will be unnecessary in the sense that they are already included into the code of previous periods. So that's why we need to compare the cycles.
So you have C1, C2, C3, C4. The index of Ci, so the index I, it doesn't matter. You just list all the simple cycles,
yes.
right? But the parameters, they depend on the nodes in the DAG.
Yes.
Okay.
So for instance, we will look at all the C3 cycle, and we want to prove that there are only finitely many choice of nodes here that give an important cycle, a cycle which is necessary, and for all the other, we won't add its weight because it will be already inside the codes of previous periods. And when a period is already in the code of previous periods, you don't need to add it. And this is where we use a reasoning which is similar to the end of the proof of Hopcroft and Pensio. So I will explain the hypothesis because there is like a lot of them. the idea is that you consider two cycles, so C is a cycle in the branching VASS. Here is a choice of node of the DAG to replace the transition plus P or plus Q, etc. And you consider two cycles which are different only by one transition is different only. Like we choose the first one, but it's not really important. You could do this for any position. We suppose that the two different nodes, N1 and N1 prime, there is a path from N1 to N1 prime. So in some sense, this cycle will be smaller than this one, and we want to prove that this cycle is better than this one, that this one will be redundant compared to this one. So to prove this, we consider a node from which possibly you could want to add the weight of those cycles to the set of periods. And we suppose that there is a path from N1 prime to M. We suppose that these two cycles have positive weights and that they are executable at the node M. And just for we write W for the weight of this cycle and W prime for the weight of this cycle. So as I said, we want to prove that this cycle has a weight which is a redundant period, an unnecessary one. So what we want to prove is that W prime is included into a cone of the period that you already have at node N1 prime, plus you add W. So this would mean, okay, if you add W, you don't need W prime. That's what it means. And to prove this, we use the same kind of reasoning as Hopcroft and Pensio. That is to say, we take the difference between W prime and W, and they are exactly the same cycle, except that they have one different transition. In the second cycle of weight W prime, you use a transition of weight B N1 prime, so the basis of node N1 prime, and in the other cycle you use the basis of the node N1. Then this difference, we do as in the proof of Hopcroft and Pensio, we say it is the weight of a cycle of the VASS, so I can decompose it. Yes, when I say the VASS, of course the VASS in the algorithm is a variable which is always changing, so you can view it as a cycle in the VASS when I treat node M, or even at the VASS when I treat node N1 prime, it's not important. And then we decompose this thing into simple cycles, and we again have the trick that every there is a path from N1 to N1 prime. This is important, so we can view this difference as a weight of a cycle in the VASS. We decompose it into simple cycles, and once again we do the same reasoning. The positive cycles will be added to the set of period P of N prime, N1 prime, and there will be this kind of reasoning with the cycles of negative effects. And with this, we will show that this difference is in the cone. So this means that this difference W prime minus W is in the cone, and then the cone is stable by addition. So I can just say, okay, this difference is in the cone. W, of course, is in the cone. So the sum is in the cone, and W prime is in the cone, and that's what we want. So that's very approximately what we do, but there are many mistakes that are made here of simplification. For instance, the cycles will not be, the simple cycle will not be executable. So this is not true. Actually, we need to use a different decomposition. We don't decompose a cycle into simple cycle. We have some more difficult but similar decomposition. And with this decomposition, every cycle will be executable and handled by the... And that's also the reason why we had to modify slightly the rule for adding period. It is so that our new decomposition will give contributions that are somehow treated by the rules for adding period. So that's approximately the proof. And the idea is that if you prove this property, you are able to compare the weights of cycles. You use this lemma several times, and you can compare the weight of two cycles, if they come from the same cycle in the branching VASS, and if for every coordinate they can be different, but there needs to be a path from the smaller cycle to the bigger cycle. So you need to have, if you have n2 prime which is different from n2, you need to have a path from n2 to n2 prime, etc. Then we show that we show how to compare the cycle, and with this minimality of the branch alpha, which gives some structure on the graph, you can use this property and show that only finitely many cycles of the VASS will create a new period. So I'm sorry if it's a bit confused, but it's really hard to explain. So the message is that we use the same reasoning as of Croft and Pensio, but in a more technical way, and we also have this kind of strange quasi-order on branches, and which allowed us to choose a good branch, and this good branch has nice properties. Basically, that's all the termination proof. So now we are at the end, and I will just make two remarks in conclusion. The first remark is that this algorithm we managed to prove termination, but we have no upper bound at all on the time complexity. The reason is that we made a proof for by contradiction, and this proof by contradiction was very virtual in the sense that we only studied objects that don't exist, that are very different from the object that really exists. We say nothing about a real execution of the algorithm. So it's very hard to convert this proof by contradiction into a complexity upper bound, even a very big one. And the second point was the question, could we generalize some of the ideas that we used for two-dimensional branching VASS to higher dimension? So of course, in higher dimension, VASS don't have semilinear reachability sets. So most of the ideas won't be generalized, but what could be generalized is the idea of studying the index of the reachability tree that are needed to reach a configuration. And the question will be, given a branching VASS, is there always a bound so that every reachable configuration is reachable by a reachability tree of index lower than this bound? So actually, I don't know if this is true or not. I have no example in any dimension of a branching VASS which would need unbounded index. So this question seems to be difficult. And if for some branching VASS you manage to prove that there is a bound on the index that are needed to reach the configuration, and if this bound is computable, then you can have a kind of construction which is vaguely similar to what we did in the first algorithm, but which allows you to prove that the reachability problem is decidable. So I cannot explain this construction. So imagine you have a branching VASS of dimension 3. No, yes, here is the underlying VASS, but somehow I needed to put the transition differently. So this transition is the same as this one. And now I would like to, from this VASS, I want to construct a VASS which has as reachability set all the configurations that are reachable in the branching VASS by trees of index at most 1. Here it is the underlying VASS, so it can reach every configuration reachable with a tree of index 0. So we'll explain how to do the construction for index 1, and then you can apply again this construction and construct a VASS for any index. So the naive idea would be to say, we do something a bit similar to what we did with linear set, but now for each transition plus P, I insert a copy of the VASS, and I have an edge which goes from the input state of this edge to the initial state of the VASS in the copy, and I also have an edge which starts from the output state of this red transition, and no, it starts from the state above. So here it's kind of difficult because I don't have many states. And then there is, yes, the transition goes from this state to this state. So here it's just from this state in the copy to this state in the real VASS. And the idea is that if you have some configuration which is reachable by a tree of index at most 1 in this branching VASS, what you could do is to reach it in this VASS. The idea is that every time you apply a binary transition, it will be something like, I am in state Q, and I want to find something which is reachable in state P, and go in state, and add the counter and go in state P. So what you could do to simulate this, this binary transition is to enter into the copy, then you compute some configuration which is reachable in the VASS in state P, and then you go back to the VASS before. And so here you can add two computations by going to the copy. So this VASS can reach everything which is reachable in this branching VASS with index 1, but this construction is not correct because the problem is that when you enter the copy to do the second run, your counters are not at 0, and so you could do something which is forbidden. So your counter could drop a bit below 0 in the computation. So you just need to add 0 tests. It's a bit complicated. You add new counters. So you have a set of counters for the real VASS, and the 3 last counters are for the copies. So in the real VASS, you don't change the new counters, and in the copies, you only change the new counters. And before leaving the copies, you have this state where you can move all of your counters to the normal counters, and if you want there to be 0 mistake, you need to check that everything was transferred. So you need to use 0 tests. But these 0 tests are not a problem because here the 3 are together, so it's like nested 0 tests, even if there are 3 counters. But this is still computable. And you could repeat if you want. Here it's only for index 1, but if you want to do a larger index, you should just insert copies inside the green copy and the blue copies.
So for index k, you would need like 3k dimensions.
Yes. So basically what we need to remember about this construction is that if we manage in larger dimension to prove that the index is bounded and to compute a bound on the index, maybe not the best one, but just a bound, then we are able to reduce the reachability problem in this branching VASS to the reachability problem for VASS with nested 0 test, and VASS with nested 0 test have a mistakable reachability problem. So that could be a way to solve the problem, but it's kind of unlikely because already in dimension 2, this index was extremely complicated to show that every VASS had a bounded index. And we didn't use the notion of index, it was just some kind of consequence of the extended Hofmann-François algorithm. So I don't really know if it is the way to go, but somehow this index seems to be a way to point exactly what is difficult in branching VASS.
But this already can be solving a problem, it's solving the bounded index reachability mirror.
Yes.
I mean, it's not just an issue, right?
Yes. I mean, it's just a new problem that we invented, so
I
it's
don't
not...
know if it is equivalent with the region
Yes.
already to speech, but...
Okay, so that's a way to formulate the results. Thank you. I think it was the end of my conclusion. So if you have questions, I'm ready to answer.
Any complexity bound?
No.
So if you have a branching VASS in the higher dimension, and you look at the underlying VASS, and its reachability relation is semilinear, is it necessarily the case that the B-VASS has a semilinear set?
Let me think. So the underlying VASS at the beginning have a semilinear reachability relation.
You take a B-VASS like the one on the left.
Yes, this one, it has a semilinear reachability relation.
Then you remove the binary rule.
Yes.
And you look at my chance the reachability relation is semilinear.
Okay. Yes.
Is it the case that the B-VASS has a semilinear?
I think yes, because you could do the iterative algorithm. So you start from this 3-dimensional VASS which has a semilinear relation. Then you add new edges corresponding to all the linear set of configuration that you reach. And I think normally this new free branching VASS, this new free VASS should also have a semilinear reachability set. and you could again apply an iteration, and then yes, but then it's not sure, it's not certain that the iterative algorithm would terminate. Like we don't know how to prove like.
But what does it mean that the underlying VASS seminar fine, but what does it mean that this binary rule seminar? Like,
well, I don't know.
There's no notion of being seminar for the binary rule.
Yeah.
The idea is that if we start from a VASS, not a two-dimensional one, but one which has a seminar reachability relation, we could do the iterative algorithm. It will be something reasonable. But I think we need to prove that it terminates, and then we have no argument for the moment.
So I get the feeling that that wouldn't work. Imagine you just take Hopcroft Pension, but you replace the loops by just binary transitions.
well,
And you allow yourself at the start to choose whether you want to go into the Hopcroft Pension copy or in some other copy where all you can do is a single step. And the binary transition will create the Hopcroft Pension loop, but at the start you were semi-linear.
Well, you can take any Petri net, add one place to it, make binary rule which is adding this place to change any transition to a binary rule. Basically.
Yeah, that's about what I wanted. Yeah, you can basically replace any transition by a binary rule, and then you have to add at the start non-determinism for choosing that maybe or so whatever it is.
It should be possible.
Yeah, so I'm pretty sure that you can create easily a branching VASS where at the start the VASS is semi-linear, but with the branching transitions it's not.
Okay, so the answer would be no. Then the question.
Just an observation. If the finite index is true,
yes,
then we have a reduction from the reachability problem to nested zero-test reachability problem. So in particular, using a recent result of you, there exists some invariance in the Presburger arithmetic, proving that some configurations are not reachable. So in particular, there is invariance for branching vector addition system that can be defined in a natural way. I mean, you say, okay, if I have some binary relation, if I take a configuration in the seminar set in both sides, I get a configuration in the seminar set. So it means that there exists inductive invariance in the Presburger arithmetic, proving non-reachability for branching vector addition system. And it will be a direct consequence of the fact that there exists finite index. But this is an open question. We don't know. We don't know if it is the case.
Okay, I'm curious about something because Hopcroft and Pension is somehow old technology, right? This person here developed a very nice notion of flattability. What goes wrong if you try to extend flattability instead of Hopcroft and Pension?
Well, flattability exactly, I don't know, but in two-dimensional VASS, you have the reachability relation, which is semi-linear, not only the reachability set, but for branching VASS, I think the reachability relation is not semi-linear.
Maybe not, but if you just care about reachability set.
Okay,
so
we just care. Yes. I don't really know, like about using flattability for reachability set, I don't really know because it was only used for the relation, so yes, we need to do some modification.
It's possible that if the reachability set is seminar, then you can compute it using acceleration techniques, so using some flattability techniques. But I don't know how to do this. Yeah, you have also this result.
In fact, I would imagine that probably if you're semi-linear, then you have the finite index conjecture and you're flattable or something. But like that would be my conjecture, but I have no idea how to prove it.
I mean, because for Petri nets with nested zero tests, when the reachability set is seminar, then it can be computed using acceleration techniques. So if the finite index conjecture is
finite index, then
it's okay.
If you're semi-linear and you're finite index, then you are computed with using acceleration. Okay.
That's cool.
Yeah.
So it's possible.
Yes.
So many people have tried before to solve this problem, me included, and like we all failed. So could you name like one or two main ideas? What was actually, what of that, what you showed us, it's technical things, and what is like the crucial step which was the point which allowed you to solve it? And what should we remember from what you said?
I think like about proving the termination of the Hopcroft-Monsieur algorithm, it was really the idea of the quasi-order on the branches, which was the very important idea. But then I don't really know, like if you just want to think without Hopcroft-Monsieur at a much more general view, it's hard to say. But for the Hopcroft-Monsieur algorithm, clearly this quasi-order on branches was the most important thing. So I don't know to what it corresponds if you try to think without this algorithm.
Yes. So yeah, there is various techniques that are used that are really independent. Some of them are completely new. And this notion of branches, minimal branches, it's really a new notion. I mean, you have a quasi-order that is not a well quasi-order, but you can find a minimal element, and this is I don't know.
No, I think it's really nice.
Of that kind. Yes. But there is also some other technical details, and it's good that you do not present the technical details. That helps proving the termination.
All right. So let's thank the speaker again.